All right, let's take a look at a more complex scenario where we've got objects that are interacting with each other. So in this case, we've got two people joined together by a massless rope. We've got Mary, we've got Dawn. And so Mary, she's got a mass of 50. Dawn's got a mass of 70. They're tied together. Dawn steps off a cliff. Mary's standing on frictionless horizontal sheet of ice. And assuming that the tree limb is frictionless, so meaning assuming that this acts like an actual pulley, we want to determine the tension in the rope and the accelerations of the two. And then we want to know what would happen if she cut the rope. All right, so again, we've got two objects now, one traveling in the horizontal, one traveling in the vertical, right? And they're moving as a system. So if we want to solve this problem, first thing you always want to do is, again, let's get a free body diagram going. So let's start with Mary. Mary's got 50 kilogram mass. There's a normal force acting on her. She has weight. That weight we're going to call mass Mary times the acceleration due to gravity. It's frictionless, right? So we don't have to worry about friction going that way. And there's a tension force in the rope. Now Dawn, on the other hand, mass is at 70 kilograms. He's got weight, so we'll call that mass Dawn times acceleration due to gravity. And there's a tension force. And we know he's moving downwards. Now, notice I didn't subscript our tension forces here. The reason I didn't subscript them is because they share the same tension force, right? If you have that rope of negligible mass connecting these two objects and it's taut, then that tension force is the same acting on Dawn and on Mary. The other thing that's going to be the same is that acceleration, right? Because, again, the rope is taut, they're acting as two objects in a single system. Now, if we want to figure out our tension forces and our acceleration, good place to always start with these problems is let's set up a net force equation for each one of these. So net force acting on Mary is equal to Mary's mass times her acceleration. Right, and the net force acting on Dawn is equal to Dawn's mass times acceleration. Right, so always start with just a basic statement of Newton's second law for each object. And then you can work them out simultaneously until you can find a bridge between the two. So for Dawn, we've got mass of Dawn times G minus tension equals mass of Dawn times A. Now, you'll notice here that I'm making downwards my positive direction. And the reason I'm doing that is just rule of thumb. Make whichever way they're moving your positive direction. That way you have to deal with a lot less negatives. It makes your life easier. Now, Mary, on the other hand, she's only got one force acting in the dimension of acceleration. So force of tension equals mass of Mary times acceleration. Now we got two unknowns in each one of these equations, right? Tension and acceleration. But we just put tension in terms of acceleration. So we can go ahead and take mass of Mary times A and plug it in here for tension. So mass of Dawn times G minus mass of Mary times A is equal to mass of Dawn times A. Well, let's get all of our unknown value on the same side. So mass of Dawn times G is equal to mass of Dawn A plus mass of Mary times acceleration. So mass of Dawn times G is equal to acceleration times mass of Dawn plus mass of Mary. So our acceleration is equal to mass of Dawn times G over the combined masses of the two. Now, what you'll notice as we get into more complex problems, I'm typically going to wait to sub in my values until the very last second. It just makes your life easier. It's harder to make a mathematical error if you're just moving variables around rather than actually plugging in numbers. So now let's plug everything in. So our acceleration is equal to 70 kilograms times 9.8 meters per second squared over 70 kilograms plus 50 kilograms. So you do the math, your acceleration comes out to 5.72 meters per second squared. Right? And again, that is the acceleration for both Dawn and Mary. All right, now that we have our acceleration, we can come back up here and solve out for our tension force. Because again, that tension force is shared between Dawn and Mary. So 50 kilograms times 5.72 meters per second squared. And we get a tension force of 285.8 newtons. 85.8 newtons. All right, so again, we've got to work a system of equations like we did in the last one. But if you always start with these two steps, right, you'll see what you have to do as you start working it out. So always, always, always get at least to this step. Actually, rather, this step before, throwing in a towel. Because here's where you're going to see how you solve that problem. Now, the last portion asks us, what would happen if she cut the rope? Well, if Mary cuts the rope, Dawn's going to fall, obviously. But what's going to happen to Mary? Well, if she cuts that rope, well, yes, that tension force here is now gone, right? Meaning that she'll no longer be accelerating, but she's still going to end up sliding off the cliff, right? Because once she cuts that rope, tension force disappears, acceleration drops to zero, but since there's no frictional force, she'll continue to move at whatever speed she was going when she cut the rope, and so will eventually reach the cliff. She's just not speeding up towards it. She'll travel towards it with a constant velocity. So she doesn't save herself by killing off Dawn, basically. Now tomorrow I'll upload a video on how to deal with forces on an inclined plane. But yeah, hopefully that helped clear up that box question on the last daily problem. Understanding that tension between your two objects are identical. But yeah, see you in the live engagement.